Okay, thanks everyone for joining this webinar in the leadership series. My name's Steve and I've got the pleasure of hosting this exciting webinar today. And I'm really excited to have these three leaders together with me. In the past couple of years, since 2022, when ChatGPT was released, the internet has been taken by storm, and many industries, including engineering and design industries, have been asking, how is AI going to affect me? How is it going to affect my role? And how is it going to affect our business? Well, that's what we're going to delve into today with this topic, with these three influential leaders in AI-powered computational design. So I've got the pleasure of being joined by Duann today. He's a great leader on the utilization of AI and its adoption. He's the founder of CDFAM, Computational Design, which is a symposium series that's been established to bring together designers, engineers, software developers, and academics to discuss computational design at all scales. I'm also joined by Matthias, and he has extensive experience of actually implementing AI-driven design in the automotive and other engineering industries. Matthias is CEO of NAVASTO, and he leads the team in revolutionizing product design and development. NAVASTO empowers companies to actually put AI into place and to optimize their products and reduce costs through unlimited iterations of their designs. And last but not least, I'm joined by David, CEO of SimScale. David is committed to empowering every engineer to be able to innovate faster by making high fidelity engineering simulation truly accessible. And with this as David's mission, we'll hear from him exactly how engineering teams are being empowered to do this with NAVASTO's technology. So it's great to see so many of you here today, and we'll get into the details in just a moment. But before we do, a bit of housekeeping. You're all on mute throughout this, but that doesn't mean that you can't send your questions in. Please do submit your questions, and we'd be very happy to answer those afterwards in a follow-up. We've got a packed agenda, so I don't think we're going to have time to cover questions from the audience. But personally, I've got a lot of experience over the past few months of working with SimScale's customers and potential customers, and I know the sort of questions that are coming up in the industry at the moment. So I'll be guiding the discussion with these three leaders so that we can go through and hear from them the answers to the typical questions that we get. Okay, so let's hear an introduction from these three first, and I'll hand over to Duann first.
Yeah. Hi, everyone. Thank you. My name is Duann Scott. I organize the CDFAM Computational Design Symposium Series, which, as Steve mentioned, brings together leading experts in design, engineering, architecture, as well as academics, which I think is important, and software developers, which is part of why we're here. As well as organizing the symposium, I'm also the executive director of the 3MF Consortium, and I teach part-time the MIT's online additive manufacturing course. The idea of CDFAM is, as I said, mentioned to bring together leading experts in the space. And originally it was more around additive manufacturing, design for additive manufacturing, but the scope quickly expanded as I saw how much exciting work was happening. And part of what I saw was a lot of misinformation around the use of AI in engineering. So some of it was delusional, some of it was deceptive, but I thought it was super important to start bringing it into the scope of the program to sort of dispel some of the myths and actually educate people about what's really going on. And that's why I was excited to have both Matthias and David at the last event in Berlin. So it's really about, CDFAM is about the multi-objective computational optimization for the performance of parts and processes, the process of actually making the objects, and the production techniques as well.
Okay, great. Thanks, Duann. And over to Matthias now for his introduction.
Thanks, Steve, first of all, for having me here. Yeah, I'm Matthias, and we at NAVASTO, we are doing what we label AI-accelerated engineering. And I'd like to take this chance for the introduction to actually go into the most important part about AI and engineering, which is the pick of the use cases. So since Steve brought up ChatGPT, this was released in November 2022, something like that. We go back
right, yeah.
about 10 years when applying AI and machine learning for engineering applications. So there was something like that even before ChatGPT. And what we're doing is in productive use by a wide range of customers. We're coming more from the automotive industry. So a lot of those logos you see on the slide is from the sector with the VW Group in Europe or General Motors in the States. These people are using the tools since many years now, and mainly because what we have built is something that was developed together with them and that is built on the experience that machine learning and deep learning is a tool that requires an end-to-end process integration and they required method developments and best practices. So this all started in essence about 10 years ago with our collaboration with VW Group Innovation. If you go to the next slide, please. Where the vision was not to replace something like simulation, but really to get people in a room together to brainstorm quickly and to make decisions within a meeting instead of everyone pitching ideas and then leaving the office to go to the desk and run simulation. So we wanted to enable them to make decisions in a room and iterate quickly. And one of the examples that came out of that is, for example, the interactive design. On the next slide, the video you see is mostly Blender, but in the back end, there is a deep learning model that can be accessed by simply clicking a button. So this idea of interactive design and disciplines working together like design, like aerodynamics in a room is what's on this screen here. So you can simply grab the mesh, modify the geometry, and instead of exporting it and running a simulation, you can query the deep learning model, you get an insight into what's happening in real time, and you can then decide what's the next best step. So this is one of the benefits, one of the use cases we see, bringing together engineers and designers. And once you have such a predictive model in place, the next logical step is, of course, to also couple that with a generative model. So if you go one slide further, exactly. So on the left-hand side, what you see is a geometry that's created using a neural network that can be exported and used directly for a simulation, but it can also be coupled to a well-trained deep learning model. So what you have here is a way to create a geometry, a way to evaluate a geometry, and if you couple that with a machine learning based optimization tool, for example, then you can close this loop and you can evaluate hundreds of geometries in parallel on CPUs, and really over the time it takes you to get a coffee, find either an aerodynamic optimum, for example, or scan the design space for possible solutions. So at the end of the day, I think the most important part when using machine learning and deep learning in the engineering context is the pick of the correct use case. And examples of that are, for example, the left shifting of physics-based insight, like illustrated in the interactive design tool, optimization and design space exploration. It's a side-by-side integration as SimScale has built it. And of course, I think in the midterm, it's going to connect the company knowledge, all the data that has been produced and is produced in those large engineering companies with the workstations of the end user.
Perfect. Thanks, Matthias. So yeah, the final introduction is over to David for the SimScale side of things.
Thanks, Steve. So Steve said it initially already. I think you said it. I'm committed to it. If you do one slide more, I think there we have it. Yes. So we see ourselves on a mission to help engineers innovate faster by making simulation truly accessible. And in that statement, yes, this is a bit of a marketing slide, admittedly, but in that statement rings that SimScale is not about one specific method, one specific solver, one specific preprocessing technology. It's about how can all of this technology be deployed into broad engineering teams, broader in engineering workflows, into the design loop to enable an engineering organization to explore the design space faster, deeper than they could before. And so for that, we started off, and still most of our usage today is on traditional PD solvers, finite volume, finite element LBM solvers. But they are deployed into the loop, and we've seen that for that, Steve, if you go one further, to effectively deploy simulation broader into engineering organizations, it's not sufficient that you just have like one well-functioning method or one well-functioning solver. It starts with the fact that you need to manage all of the data that's being produced, and then you need to manage user and processes around it. How can you enable a program engineer make informed design decisions without knowing which specific simulation method has been used? So there's a piece to like process management and governance, which we can see in the top right, user and process management. Then all of that needs quite a bit of computational horsepower, depending on the method, depending on how many simulations you want to run. So you need to build in HPC management, HPC provisioning. And lastly, typically many different physics do govern most of the modern products that are being developed. And so that's the platform we've built with SimScale. So a unique vertically integrated simulation platform that brings all of this fully integrated and not user data process management as an afterthought. And so what our customers then are empowered to do is they build out simulation workflows centrally, then they can deploy them broadly with this user data and process management. And now it turns out that in order to deploy simulation broadly, there's very similar requirements to deploy AI-accelerated simulation workflow in a similar way. So because you also need to manage data, you need to manage processes, you need to start maintaining or managing an AI model lifecycle. And so it turns out that the basis for these broad deploys of simulations is also a fantastic basis to deploy actually AI-accelerated workflows. And that was really sort of for us the starting point with our collaboration with NAVASTO, integrating NAVASTO's technology into SimScale in a native way. We're going to see it later in action. And Steve, if you click one further, because what's now happening on SimScale is that all of the data that's being produced along a simulation process, from CAD over CAD preprocessing, physics setup, meshing, result generation, yada, yada, all of these steps generate data. Wait, Steve, not this fast. Maybe I'm doing too much hand waving. All of the data, because SimScale is cloud native, lies in the cloud. And so everything is now there, structured in databases, accessible, properly versioned, etc. All is there. And right next to it is practically unlimited compute power GPUs to start now, tapping into modern ML techniques to train that. And so all of this is now aggregated, ready for training. And so what we've built over the last couple of years is, Steve, now if you go one further, is a couple of first steps of how AI can accelerate the simulation process. And on the left, we can see resource prediction. So since actually a number of years by now, SimScale users do not choose the compute instance themselves, but an AI model is actually choosing it based on the simulation setup in the CAD model. And now in the collaboration with NAVASTO, we have now results preview AI simulation available, where the physics is being evaluated with NAVASTO technology based on an AI inference with a neural net and not on a PD solve anymore. And moving forward, there's more potential to accelerate the process, where we have sort of on the left, of course, helping in pre-processing CAD and mesh generation, as well as simulation setup suggestion, as well as something like Matthias showed, like design insights, as to evaluate the actual design performance and sort of inform sort of the next iteration. And so we are fundamentally convinced that probably, most steps in an engineering workflow, and this is really sort of today, Matthias and me are, come from the simulation space. Duann will cover this a bit broader, that in the broader engineering workflow, many of the tasks will be augmented or accelerated or fully automated with AI techniques. And the way we think about it is that because SimScale is in the cloud and we're sort of focusing on the simulation workflow, every step here in the simulation workflow will eventually be AI augmented. What we're going to see later, Steve, one last slide. And so we're excited about the AI integration with NAVASTO, where now so far we could do cloud native partial differential equation simulations. And now as an engineering team starts producing naturally this data with standard PDE solvers, Steve, one more, then suddenly more and more data is available. And because it's already there, it's not an IT project anymore. It's not like a huge data gathering effort anymore. It all sits in the cloud next to compute. We can leverage the data with the integration with NAVASTO and directly train deep learning surrogates and evaluate physics in real time. And that's, I guess, like our point of view on all of this. that SimScale, again, is not about a specific method, but how does a modern simulation stack need to look like in order to actually unlock broad simulation and eventually also AI accelerated simulation.
Brilliant. Thanks, David. So yeah, I think for the audience, that really helps to understand why these three people are here today for this discussion. And what we're going to do is now, I want to take you through a few questions and go down a few avenues of things that people are typically looking to understand in this space. And the questions that we're going to look at are, what are the common concerns, challenges, and fears associated with AI? There's many leaders in computational design wondering when the right time is to implement AI and wondering if they're ready for it. And they're going to want to know how they can get started with AI, how they can actually put the processes in place. A common question that we get virtually every time we show AI in action is, how much data do you really need for this to work? And we'll look a bit more philosophically at a question that everyone wants to know is, how is AI going to impact design and simulation in the next decade? So in order to do this, I initially want to start quite broad on the discussion here. And we're going to consider how AI is impacting digital design. For that, I'll hand the question over to Duann in a moment. And then once we've covered more generally how AI is going to impact the industry, we've got Matthias and David to delve a bit deeper into how exactly AI can be used. And specifically, we're talking about graph neural networks and machine learning models for engineering simulation. AI is such a broad topic. So firstly, Duann, how do the CDFAM attendees consider AI, and what do you feel are the common concerns and fears associated with AI in the industry?
Yeah, I think what's interesting, as David mentioned, the data collection and preparation. So I think a lot of companies feel like they're being they're kind of flat-footed when it comes to have preparation for adopting AI, and the fact that using SimScale kind of automatically starts capturing that data and preparing it is interesting. So there's an interesting chart by a researcher called Monica Rigatti, which is the data science hierarchy of needs, which talks about the need to go from collecting to moving to storing to exploring to transforming to aggregating to learning to optimizing, and then finally you can actually start using the data. And that sounds like a lot of work, right? It sounds like a lot of, and someone has to choose the right data to use into that. And I think this approach of like starting to use tools like SimScale in the cloud, you're sort of like doing the work for free while you're preparing existing designs. So I think there's a lot of potential with that, which I hadn't really thought of in the same way before. But what I've seen so far from most of the attendees and participants at CDFAM is a lot of them are at the very early research stage, unless they have a very, very specific application. So I'm seeing a lot of research around exploring GPT and VLMs for doing 3D geometry, and they're primarily failing pretty hard because there's no spatial awareness in these tools, so they can't really get things moving. The next thing I'm seeing is really defined research in using machine learning to predict like lattice structure performance for 3D printing, because it's a gnarly problem to solve, and comparing between two different lattice structures and how they perform is very, very difficult with different materials. And then the third one I'm seeing sort of adoption now is in the dental space, where you have things like aligners, where everyone's sort of kind of similar, but different. And so using machine learning to interpolate between those different requirements as you guide someone's teeth into Tom Cruise shape is something that they can do easily, you know. So I think that's where I'm seeing adoption. And honestly, NAVASTO was the first one software that I've seen that I consider to be more open and ready for use than anything else I've seen to date. So that's why I'm so glad that he could participate at CDFAM in Berlin. And the response was a bit of skepticism, because people who have been doing simulation for years, like decades, feel like it's too good to be true. And so that's why I was super happy to have him present.
Yeah, I think there is a lot of skepticism right? People have seen AI come along quite a long way in the last couple of years, and certainly I think there's a bit of a fear that AI is going to be doing the most exciting side of things. It's doing the creative writing, it's creating the artwork, but really what we want AI to be doing is taking away the boring, repetitive tasks that we have to do, right?
Exactly. We don't need artists replaced. We need bureaucrats replaced.
Exactly. So yeah, I think AI, in a sense, it feels very new to many engineers because of the big advancements we've had in the last couple of years. And I like to compare it to the advent of the internet, where things are all of a sudden being revolutionized by AI. But it's really interesting to hear your input, Matthias, about how exactly you've been doing this for a decade now, implementing these technologies. And to many people, it's so new. How would you advise that people really get started with AI with your extensive experience you've got of actually implementing it?
Yeah, absolutely. So first of all, the perception of AI or machine learning has changed drastically over the past decade. When it started talking to people about using machine learning models for engineering data, people simply didn't believe that this is doable, that it's possible, that you can get something useful out of a prediction. And actually with ChatGPT, this has kind of changed by 180 degrees. Now, when I talk to people, it's more about expectation management because it's still not a magic trick. So the very first use case that we implemented was with an automotive OEM, and same problem there. The machine learning predictive part was kind of, well, we're not sure, but optimization is something that we're interested in. So we built an optimization process there that produces simulation data as part of this optimization loop. And they could run an optimization for a specific target function. And on top of that, we computed a machine learning model that was able to predict the result for new geometries based on the data that they already generated during the optimization loop. So this is kind of how we sneaked in this technology at the very beginning. And the interesting part was when we ran the optimization, we came out with an aerodynamic optimum. And if you would only have done an optimization, then this would have been your result. So that's the position, use that, that's the aerodynamic optimum. But it turned out that from a structural point of view, this was suboptimal. So with the help of the machine learning model, they could then interactively search for a second good solution within the design space that was still almost identical in terms of the aerodynamic performance, just a little tiny bit worse than the actual optimum, but much better from a second perspective. So this is where the value of such a solution actually becomes apparent, because the human is still in the loop. It's far too difficult to actually define and design a target function that respects all those different disciplines. But with the human in the loop and the fast response of a machine learning model, you can search and work well, build something that's better than with the conventional tools. So to go to the question back directly, how do people get started today? Well, mostly, I think it's a new tool, and those who realize that this is one other CAE tool, they simply get started. Like the question is, how do you get started with simulation? Well, you try and see if it works for your problem. And by doing it, you learn where the limitations are, you learn where the added value is. So I think we are getting started just like anyone else is getting started with simulation tools, if someone has committed to give it a try and involve the relevant people. So the ones with the domain expertise to train models, and more specifically to judge if this is a good model, and the ones that are supposed to use the model in the productive process. And yeah, from there on, it's pretty obvious that this is adding value to the toolchain.
Yeah, and it's really interesting what you say about the misconceptions there, Matthias, and the expectation management that you have to set. It's certainly something I've seen as well with many of our prospects. They almost expect this to be a magic tool that works with any geometry, any set of boundary conditions that you put into it. How have you seen that, Duann, in your space? Do you see people having misconceptions about what's possible and what they can do?
Yeah, similarly, I think that the advent of GPT has got people super excited and sort of not looking at the details of what it really takes to do things in a narrow way. I think if you start asking GPT specific questions about something you know about, then you'll quickly realize that it's wrong. But I think that it's sort of got people thinking that maybe these tools are possible. So I think most people at the early exploration stage that I'm aware of in adopting these tools, and as I mentioned, thinking about collecting the right data, which I think is a core problem for people.
Yeah, definitely. So kind of to move on from that, and David, to ask you specifically, what can we do to alleviate those concerns? You alluded to the fact that with SimScale, you can collect the data and collate it together. How can we help our customers and engineering companies to get over that hurdle?
I liked, I guess the way I would sort of unpack that is, I like what Matthias said earlier, like the very sober view on, you know, like AI is not a hammer where, you know, like you hammer it on everything. No, there's a certain time and place for a specific method. And by the way, I mean, it's the same like PDE solvers. Is, you know, like typically an engineer that doesn't get away with a single PDE solver that solves everything, right? Because for a specific problem, you need a specific tool. And I think it's the same with these methods. And we've been always, I mean, Steve, you will know, we've been always guiding our customers that if you tap into broader user simulation, you don't start, you know, with right away, like overnight deploy to hundreds of users. It's more like you lay out a path and you prove out impact after impact, and you sort of bring on more users, more use cases, and that's how you do that, right? But you have sort of this maturity, this sort of path in mind. And I think, again, it's very similar to this, where what we've been talking to our customers about is, since you start generating that data in the cloud and it's there, the hurdle to just simply look, just take it, train a deep learning surrogate, see if it creates value, or even better, Matthias, I think you used to say, like, you start with the use case, like where's a bottleneck in your engineering workflow? Like where's a strong bottleneck that would either, is it an optimization, or is it where you really want a design engineer to get through 20 design versions in like 10 minutes, right? Then you need an AI method. And so for those situations, you just like get started, train it, and we make it easy. That's, I guess, and for us, I think the conversation has been very similar to how we've been guiding customers on using simulation in a broader way. I guess that's how we're thinking about it.
Yeah, I think that's really interesting because, as we've discussed, AI is nothing new, right? Everyone knew about neural networks and AI for quite a long time now. And personally, I always considered it to be a specialist tool. I've got friends who are data scientists and have been working on this for a long time. But coming back to ChatGPT again, that was something that really revolutionized the access to AI. Before that, nobody had a large language model running on their phone that they could just talk to and use, but they really made it available. And that's something similar to how AI is now being made available for digital engineering. With SimScale, you don't necessarily need to have a large team of data scientists to actually get things set up and working. Can you tell us a bit about how you can actually get started, David?
And Steve, you need to moderate that, right? I need to talk about SimScale. You need to moderate today, right? Just saying, not funny. Okay. Yes, I mean, when in the very first conversations with Matthias, I think like a sentence he said, and Matthias, I'm not sure if you remember saying that sentence, where he said, you said something along the lines, in the past, like all simulation results would get a report, right? Like all simulations result would be an input to a report. In the future, maybe even all simulation results will be an input to a deep learning surrogate where you sort of train a model with it. And I think back then when we talked about it, I didn't get that yet. By now I understand. And Steve, to your point, on our journey, years ago, sort of starting to integrate AI models into SimScale, we of course had appreciation for DevOps. I mean, we're a software engineering team building software for hardware engineers, and so we have an appreciation for both of those worlds. And so as we delve into that sort of, the notion of MLOps and data engineering and all of those sort of things you need to, be good at to deploy machine learning models to production. Again, Matthias will have an appreciation for that. Duann, is sort of that complexity is something that's, I mean, I'm a mechanical engineer by training, wasn't clear to me. And so as we sort of saw what it takes to deploy an AI model to production, and making sure that you can maintain the life cycle of that model, which data went into it, you have sort of traceability, yada, yada, yada. That's something mature engineering organizations maybe can do on site, right? And sort of SimScale takes a lot of that complexity and sort of like simply sort of manages that for an engineering organization. So at the end of the day, it's, again, I would take again the analogy of what we're doing for simulation, process, and data management, right? Like we're doing part of that MLOps and sort of doing it, like taking it away from the customer, and so that the customer does not need to deal with all of that. And so in essence, it just lowers the barrier on, look, you get like 100 models simulated that are similar. That is a simulation you would actually want to run an optimization, or that's a sort of design space exploration that you actually want to sort of navigate quickly. You can do it much quicker because a lot of that complexity is abstracted from you. Again, maybe I'm repeating myself, but for us, like the analogies between deploying simulation broad and deploying AI accelerated simulation broad has been just very, very fruitful, and hence also the collaboration with NAVASTO.
Yeah, exactly, and it makes sense, right? There's the infrastructure there to be able to access it, and there's the brains behind it coming from NAVASTO and making that available to the masses. So yeah, in my experience, whenever we present AI, there's always a lot of skepticism around it until you actually show it working. And then the penny drops and they understand. And the next question that comes is, what about the data? How much data do you need? How broad does the data set need to be? How narrow does the data set need to be on specific items? So I'd like to put that question to Matthias and to Duann afterwards as well, about how the community considers it. So first of all, Matthias, how have you addressed the data topic with your big automotive customers?
Yeah. So, I mean, to this question, there is no simple answer. How much data you need depends on many factors. The complexity of the geometry that you want to model, the accuracy of the prediction you expect compared to the data source, the means of sampling that were used. So there's a difference if you run a design of experiment where you sample a parameter space or a design space so that it's space filling, meaning every part of the design space is covered, or if you run an optimization, or you simply take the data from the regular development process where a lot of different people just run different simulations and you have to consume that. And then of course it's also a question of the non-linearity between the input and the output. In practice, for an automotive use case, something like 30 or 50 samples can get you started to train a first model that's going to be a model that's useful, maybe for a specific task, or at least to demonstrate how the process is working. And maybe touching back to David's answer a second ago, I think the most beautiful thing of this technology being deployed on SimScale is really the fact that most of our work is not in tuning machine learning and deep learning models. It's building this end-to-end pipeline at customers that have all different data structures and different end use cases. And with SimScale, this is just that since you own the data structure and the front end where it's consumed, it's just perfect for this kind of technology. So in terms of data, in our practical experience, very often we get started on something like that. 50 samples, 100 samples, 150 samples, either produced specifically for the task or they just found something lying around. But this is the starting point. From there on, what we encourage our customers to do is to grow models. So whenever a new data point becomes available, because your machine learning model won't replace simulation. So you're gonna still continue to simulate, and whenever this data becomes available, you add this new data point to a model when it makes sense. And over time, this model simply becomes more and more capable. And in our experience, the OEMs run a lot of simulations thousands of DFT simulations a year, hundreds of thousands of crash simulations a year. So data at some point is not really the issue. What's important is really getting started with training models and deploying models so that you know what your end user actually wants to have. And at the same time, realize which type of data you have to save, in what structure you want to save it, and make clear to the engineers that produce the data that they are responsible for the quality of this data. So all this, I need a data scientist to analyze my input data, kind of is less relevant in a actual OEM style process, where people are aware that the data doesn't end in a report, as David mentioned, but this is potentially something that's going to be reused, and thus they see the value of really making sure that good data is saved and at least marked if a solution didn't converge or something like that. So in a summary, there is no simple answer to how much data you need. In practice, there is so much data available. At least if you start saving it in the right way, that the data problem kind of solves itself.
Well, I think this is like talking to what, to me, computational design is about. It's about designing the system to make the solution, not just designing a solution. So in engineering school, you're sort of trained to narrow down until you get something that fits the optimum, whatever that may be, and then you're done. You sort of the wall to the manufacturer, and you move on. But in this scenario, what you're designing is a system so that you can make future designs based on the groundwork you're doing now. I think that's what's critical. The second thing I wanted to touch on is that I think early on people misunderstand the difference between interpolation and extrapolation from those data points. So Matthias, can you talk about where it sits, like inside or outside the boundaries of the data you have?
Well, that's a very interesting point. So machine learning and deep learning in general works very well on interpolation, and it does not really work very well on extrapolation. You can be lucky that it works on extrapolation, but I wouldn't bet on that. So in practice, since this is an engineering tool, one of the most important things to make available to the end user is a way to judge if you're interpolating or extrapolating, and even if you're interpolating, what the uncertainty of such a prediction is. There is no clear analytical form to compute my solution is going to be 5% off of a baseline. By the way, what's the actual baseline? What's the ground truth? Simulation is not really a ground truth. An experiment in a wind tunnel is not really a ground truth. Even if you have a car on a street, the performance might change with the age and stuff like that. So nevertheless, you need to give your end user a tool or a metrics at hand so that they can judge if this prediction is trustworthy or not. And if it's not trustworthy, they have to run a simulation or experiment or whatever. But if the prediction is trustworthy, if we are doing interpolation in this sense with a well-trained model that's suitable for the specific task, then you can iterate very, very quickly.
Yeah, that's really great. And on the same lines as that, Matthias, how does the graph neural network technology assist with that compared to a more traditional neural network?
I try to avoid to talk about methods, specifically for the reason that, not because it's secrecy or something like that. I believe everyone that's doing that today is basing their work on something that Meta or Google has researched and published. Graph neural networks have a huge advantage in this field because they don't only have coordinates in them, but also edges that connect the coordinates. It's a mesh that we learn from, either a tessellated surface coming from a CAD tool or the mesh that was used to run a simulation. So this additional information of the edges allows the neural network to learn better because it knows in which direction information can pass. But apart from that, it doesn't really matter if it's a graph neural network, if it's a point cloud transformer, a 3D convolutional neural network. All of those tools have one advantage over the conventional machine learning methods, and this is the fact that they can learn on non-parametric data. So you can learn directly on the shape, meaning you don't have to parameterize something beforehand and eventually run a design of experiment, but you can really consume the data that was produced in the past. So this is the main advantage of the modern deep learning frameworks that are commonly being used today to predict on engineering type of data.
Great, thanks. So I think one of the takeaways that I would take from this is that the data scientist role isn't necessarily absolutely critical for the implementation of AI. And normal engineers can really work to implement an AI-based machine learning solution. And if we really are ready to implement it, how do you envisage that design and simulation is going to be influenced by this over the next 5 to 10 years? So starting with Duann from your symposium members and the thoughts that you hear.
I'm going to go back to like a dumb version. So old enough to have used analog cameras, and when you send film off to be processed, the feedback loop is 2 weeks. You go, okay, that was terrible exposure, that was terrible time. There was terrible lighting, terrible composition, and trying to learn how to take a good photograph. Once we had little cameras with instant feedback, you quickly learn how to frame things, how to get the lighting right. If you had aperture and shutter speed, then you could figure that out. And so the feedback loop for learning is very, very quick. So if you look now on Getty Images versus, I'm going to say Flickr, I don't know if that still exists, the difference between a professional photograph and an amateur one is very, very close. I think by having these feedback loops very fast in the design iteration, we can improve our designs very, very quickly in a way that isn't analog.
Yeah, and I think the analogy with traditional cameras is fantastic because no organization wants to be a Kodak model. Everyone wants to move with the times and ensure that they're keeping up with innovation, right? And I think that's part of the fear that comes up with new technology and innovation. David, how about you? What are your thoughts on that?
I don't have such a nice analogy as Duann. I should have thought about one before, but maybe just to end on a higher note, I think like we've been dedicating our professional careers to simulation and sort of that, and that's admittedly a narrow part of the engineering workflow. It's sort of evaluating the functional performance of a product. And I think like what I've seen left and right among others via the CDFAM community is that I think like as we're I think we live in an exciting time where sort of all the data that was sort of stuck in PLN systems, SPDM systems, etc., is being now brought out of the silos, connected to each other, and and the awareness is there that this data will be very, very helpful in whatever workflow that will happen. Today we talked a lot about sort of accelerated physics prediction. There's more that I think will come out of this, and like there's I think exciting companies sort of pulling out this data and training very, very exciting models to eventually accelerate or eventually automate the entire engineering workflow. And so that's why, and we're just doing our small part on the simulation part. And I think we live in a very exciting time where hardware design is fundamentally changing, and couldn't be more excited.
I wonder if data in the past was purely to cover your ass, so if something went wrong, you could point to and say, I did the right thing, but now can
System of record.
Good. We can use it to make.
Exactly. I think you can really start to leverage the data now as well. And yeah, Matthias, what are your expectations in the next 5 to 10 years?
I mean, 10 years is distant future. I love the example of Duann, the 2 weeks with the camera. The first video I've shown, the one with the car and the blender and the inductive design. This was requested by OEM that described the problem to us coming from the design department, from the automotive design studio, that they have a design that they're happy with aesthetically, but then they need to export the geometry, hand it over to the aero department, and with data pre-processing and solving and report generation, they told us it takes 2 weeks to give them an answer. The problem is very simply that the designers didn't stop working those 2 weeks. So once they got the answer 2 weeks later, the design they had on their screen by that time was evolved to a point that the answer they got from their question 2 weeks ago was correct potentially, but less useful than it could be. So this is exactly what's happening. It's this left shifting. It's making available information early in the process. Where I see the technology going today for the next years, maybe not 10 years, maybe rather 2 years or 5 years, something like that, is that it's going to connect the entirety of the available engineering data with the end users, with the engineering workstations, so that data doesn't go to waste. I had a call with a prospect today, and they literally told me, we are running so many simulations, we are certainly not exploiting this data to the best of what we can do. And then we have to delete it at some point because simply there is no space anymore. So this is something where I think machine learning, deep learning can bridge this gap between a corporate knowledge base, which is in essence all the simulation data, and the people that are in need of physics-based insights early on in the process. And even if it's only, has someone of my colleagues 3 years ago solved a similar problem? What was the answer back then, and what did they do afterwards? So this is something where I see that machine learning and deep learning is currently built to do, at least with the large organizations.
Yeah, I think that's really insightful, and I'm looking forward to and excited to see what the next 5 to 10 years will bring, because we've had huge advancements in the past decade, and I can only envisage how far things are going to come. So yeah, to sum it up for the audience, I think we're ready to get started. You should be ready to get started with AI today. The best thing that you can do to start preparing is to use a simulation tool that catalogs your data in a way that you can leverage it and use it in the future for AI. And we really are living in the present, and it's available now. It's been there for over 10 years, which I think is absolutely incredible. So thank you for all the questions that are coming in. Unfortunately, we don't have time to answer those live now, but I would like to spend the last 5 minutes to just show you how this works in real life on SimScale. I've tried to stay impartial through this, but I am a SimScale representative at the end of the day, so I'd love to give you a demo of how it actually works. Okay, so if I go to simscale.com, I can obviously access all of my simulations, etc. And for this example, I'm going to use a bracket, and this is a suspension arm bracket where maybe I've got an initial design, a concept design purely with the shape. And I can leverage the fact that I've done many simulations of similar brackets, and I've built a machine learning model running on NAVASTO's technology so that I can predict what the stresses are going to be on this part. And I can very rapidly iterate through the design, make changes, and assess how that's going to impact my part. So I can see here the von Mises stress. I can see I've got an 88% confidence rating. So I know that this isn't necessarily extrapolating outside of the data set that I've got. Talking about what Matthias was saying, you need a measure of how good the data is. So say, for example, I want to do some what if scenarios on this bracket, and I could see that the stresses were fairly low there. So I might want to actually edit this geometry and save some mass and save some material by reducing the size of this by 5 millimeters. So I can do that live in SimScale. I can adjust the geometry, and then I can swap out my geometry for this alternative so that I've got the new geometry and have the AI prediction live on that. So I can really make rapid changes through the design, swap out the CAD, and then immediately get a prediction of what the stresses would be on this new geometry without having to swap out to CAD tools, without having to spend a long time creating new iterations. So I can see there obviously the changes in stress that I've got on this part, and I can make much more drastic changes as well. So say, for example, I wanted to remove some material from areas where I've got a relatively low stress region in this part. I can quickly make changes, I can change the material, I can change the forces and boundary conditions, and make informed decisions about how this is going to affect the stresses on the part and get an understanding of what I can do to optimize this design. So we've gone from a very simplified, basically near net shape part. We've changed the thickness and we've added some cutouts in the low stress regions. And then we can see a much more advanced geometry with the stress prediction live on that. So we've got a much more optimized part. We've added in the fillets, and this is quite different from some of the training data. So you can see we've got a slightly lower confidence rating. So maybe in order to get a much higher confidence rating, we need to build some more simulations into this model, but we could very easily run those live now in SimScale. I could start a simulation, and when I've got that result back, I just feed it back in to the machine learning model. Now, I'm sure you're asking how accurate this is. You know, that's fine that we can do all of that in seconds and we can iterate through the design, but what's the side-by-side comparison? Well, on the left-hand side here, you can see the PDE solve of this bracket, and on the right-hand side, you can see the AI prediction with the same scale bar. And you can see that 95% confidence interval is really accurate. We've got an excellent prediction of the stress fields on these parts. So you know if that confidence interval is high, you can trust the data. And this is obviously physics agnostic. So whatever simulations you run in SimScale, you can also use the NAVASTO prediction to predict what those physics would be. So here we can see a radial pump model. Again, the left-hand side is the PDE solve CFD in SimScale, and the right-hand side is the AI prediction. So very good correlation between the pressure fields. Okay, so super quick demo, but AI is super quick. So thank you very much for your time. It's great to see so many questions, and we'll come back to those. As for next steps, you can sign up to SimScale today. You can request a demo. You can contact me directly. You can contact sales at SimScale. Just go to the website and you can get set up and going. Also, I'd like to hand the stage to Duann for a second to talk about the next symposium that's coming up.
Thanks a lot, Steve. Yeah, so the next event's happening in New York at the Brooklyn Navy Yards at New Lab, October 2nd and 3rd. It brings together about just over 30 speakers who are experts in computational design at all scales, from engineering designers, architects, academia, and software developers, and really to talk about what's emerging now, what's cutting edge, and what's in use. So if you're interested, I try and run these events twice a year in the US and Europe. CDFAM.com, check it out, and hope you can be there. If you want to present, if you're doing something cool, just reach out to me and I'll have a chat. Thank you.
Brilliant. Thanks, everyone. Thanks for your time. Bye.
Thank you.